get into the numbers. Okay. So let me begin now introducing the speaker in the seminar series. So actually it's 3 p.m. So let's begin. I'd like to welcome everybody back to the online SPICE-SPIN+X seminar series. Once again, this is a joint effort between the Spin Fundamental Interdisciplinary Center that I lead together with Karen Eversource City, and the SPIN+X Collaborative Research Center between Kaiserslautern and Mainz that is led by Martina Schliemann, Burkhard Hillebrands, and Matthias Chloe. We have this every Wednesday. We're trying to have this every Wednesday. It is a webinar format, meaning that these attendees cannot speak at the moment or share their screen, but they can ask questions and write the questions down. I will ask you to write the questions down during the talk and leave them on, because I will then later on give the microphone to each of you to be able to ask directly to Amir Yacoby your own questions directly to him. Of course, if there is some abusive questions or something like this, I will stop that from them and kick you out, unfortunately. But you have a very nice lineup. Next week, for example, we have Juliette Grelier talking about neuromorphic computing type of things, and Christian back the week after. Then just a few words, I would like to say, a few words about Amir Yacoby, and we'll begin immediately. Amir is one of the best speakers I know, a fantastic physicist, and the type of physicist that makes extremely hard experiments and how they do it seem easy, which is amazing. That's what makes beautiful physics. He had his PhD in the Weizmann Institute in '94, had a postdoc spell in Bell Labs, and then went back to Weizmann as a professor. And then in 2006, he started at Harvard University. Is now Lazari's chair of the Physics Institute of the Institute of Quantum Computing. He's interested in many things, but particularly he's now really pioneering metrology at the highest level, with including magnetism and spin physics and quantum spin physics as well. One of the main impacts that he had as a postdoc, for example, was the first observation of the spin charge separation in mesoscopic wires that made him overnight famous, and then he's been pioneering things ever since. And if you actually go to his website, you see these beautiful graphics like topological systems, graphene, NV centers, and spin qubits, and a very broad aspects that he's going to share. So with this, I'll stop sharing my screen. And then I'll ask Amir to please go ahead and share your screen. And you can begin whenever you wish.
Okay. Can you see my screen properly?
Yeah, we can see your screen very well. Oh, and now we see the screen, but from the presenter point of view, can you switch it? That is actually the other way.
Yeah. Okay. Give me a sec.
You just have to do the switch to the... I think on the top you can say that when you... Coming up. Double click to share. No, I see Amir has started sharing. Double click. Yeah, now it's beginning to show up. Yeah, that's perfect. Go ahead whenever you want.
Okay. So I'd like to start by thanking Cairo for inviting me to the seminar series. I've been following it and really learning a lot of exciting physics. I want to thank the entire panel for giving me this opportunity to tell you about some of the recent work that we've been doing with the purpose of developing new measurement techniques. Specifically in this talk, I'll cover the use of magnons as a new probe for correlated electron physics. Now, I'd like to start by giving a little bit of an overview why I believe the time now is right for developing new measurement techniques. And you might ask, well, why would I do that? And since obviously we do have a tremendous tool set for exploring strongly correlated physics. So why do we need to develop new techniques? And I'd like to give just a handful of examples that will hopefully highlight some of our own interest in trying to unravel some of the challenges that recent discoveries in mesoscopic, strongly correlated topological physics have challenged experimentalists. So starting with ground state properties, I'm showing here 3 systems in which there are some interesting physics that, however, present tremendous challenges for experimentalists to observe. On the upper right, you see something that we're all familiar with, which is a 2-dimensional topological insulator. This system is gapped in the bulk, and as a topological insulator, it carries surface states. These are 1-dimensional edge states that are chiral. One spin species is flowing in one direction and the other is flowing in the other direction. Now, this is a steady state ground state property of the system. And obviously the fact that you have 2 counter-propagating edge states means that there is no net charge current flowing at the edge. But if you look carefully, you see that because one edge state carries one spin species and the other the opposite, this means that in steady state, this system actually carries a spin current. However, we really don't have any tools today that allow us to explore the presence of this steady state spin current. So how can we confirm this notion of a steady state spin current in equilibrium? In the middle here, I'm showing another interesting ground state, proposed ground state that is believed to exist in twisted bilayer graphene. This is a system where you have 2 sheets of graphene stacked one on top of the other with a small angle. One of the insulating states of that system is shown here, consisting of plaquettes of current that are counterclockwise, clockwise, and no net current. The length scale for which these currents persist is roughly the atomic scale, so let's say of order a nanometer. And again, they exist in equilibrium, but here again, we don't really have any tools that would allow us to see or verify that such a ground state exists. And on the bottom left, I'm showing a suspended graphene sheet. This is in pink here. And it turns out that its strong magnetic field, this system actually develops a antiferromagnetic phase. And I'll talk more about this throughout this talk today. And the challenge here is the fact that the volume of this magnetism is very, very small. We do have tools that allow us to explore ferromagnetism and antiferromagnetism, such as neutron scattering. However, the challenge here is that we have a monolayer of material, and also the magnetization density in this system is roughly 1,000,000 times smaller than what you'd find in a conventional metal. So our existing techniques are just not sensitive enough to realize that such a phase exists. And again, we're challenged with how do we figure out whether such a phase exists in this material or not. Now, going beyond the ground state properties, one can ask about excitations. So what lives above the ground state? And here I'm giving, again, just 2 examples of some interesting excitations that we know should exist in some modern condensed matter material systems. The first is spin liquids. These are materials that are highly frustrated magnetic systems where magnetic order does not set in principle, down to 0 temperature. But the excitations of these systems do not carry charge, but they carry spin. And I'll talk about spin excitation, spin waves throughout the talk. I'll be talking about bosonic spin excitations. In spin liquids, actually, these spin excitations are believed to be fermionic. And again, we don't really have any tools that allow us to neither detect or visualize or explore the properties, the density of states, etc., the occupation of these spin excitations. Another example is an excitation that exists in topological superconductors. These are materials where the bulk of the superconductor is gapped as any conventional superconductor, but topological superconductors, again, carry edge states, and these have interesting properties, in particular non-abelian characteristic. And again, we lack tools to be able to identify, detect, and confirm the presence of such non-abelian excitations in topological superconductors. Now, if we have a system that has some interesting excitations, and these excitations are even long-lived, then one can start asking questions about transport of these excitations. If excitations are long-lived, we can talk about their chemical potential, and gradients of chemical potential of these excitations would drive currents. And here again, there have been some beautiful theoretical proposals about the transport of interesting excitations. For example, here, some theoretical proposals about superfluid spin transport through easy plane ferromagnetic insulators. Another interesting development has to do with quantized thermal Hall effect and other type of universal properties that could exist here. This is thermal excitations for not phononic excitations that exists again in spin liquids. So hopefully this picture that emerges is that indeed developing new methods for exploring quantum matter is really necessary. And I have to say, this has been something that's been defining my personal career, is always figuring out new ways to look at materials and then using those to discover new physics. This new physics usually fuels our ability to develop new novel techniques, and the cycle continues onwards and onwards. So in today's talk, I'd like to cover from kind of high above. I won't go too much into details, but two generic topics that we've been working on intensely throughout the past several years that involve the use of magnetic excitation, spin wave excitations, to explore the underlying ground states of various materials. The first topic will be a low temperature, high magnetic field premise, where we'll be looking at magnetism that exists in quantum Hall systems. So I'll describe how quantum Hall physics is responsible for generating magnetic excitations and what are the challenges in exploring these magnetic excitations. The second part of the talk, I'll try to generalize the concept of using magnetic excitations for exploring quantum matter and show where we are currently in the use of NV center magnetometry for really doing some novel scattering experiments to unravel underlying microscopic magnetic properties of materials of mesoscopic dimensions. So let me begin with the quantum Hall physics. So I'm sure you've heard many, many talks about quantum Hall physics. Most of these talks involve edge state transport. Today, we'll use edge states as the means to excite bulk excitations, but the focus will not be on edge states. And I want to remind you, first of all, that quantum Hall physics is a system that is a phenomena that emerges when you take a two-dimensional system subject to a very strong perpendicular magnetic field. And what we've learned over the course of many years is that it is really rich. It has many different underlying excitations, and here I'm showing a few of them. For example, near filling factor 1, we have skyrmionic excitations. These are charged particles that carry novel spin topological textures with them. Near half filling, we have composite fermions. These are particles, again, they're charged. They carry a charge E, and they carry 2 flux quanta of magnetic field with them. At fractional filling, we have fractional charges. And of course, even at half filling, we can have a situation where the system develops an analog phase to a topological superconductor, and there the underlying excitations have non-abelian statistics. Again, in that phase, the system has a charge of E/4. So what is common to all these phases, as you can see, is that all these excitations, which are really a result of strong interactions in the system, are charged. But what about neutral excitations? It turns out that neutral excitations do exist in quantum Hall systems and have been realized and discussed theoretically a long, long time ago. Here, I show a review article by Steve Gervin, a theorist currently at Yale, from Physics Today 2000. where he writes that at filling factor 1, spin waves are the lowest energy excitations, but because they do not carry charge, they do not have a large impact on electrical transport properties. So already a challenge is that since we're used to probing quantum Hall systems through electrical transport and these excitations are neutral, then how can we observe them? The second challenge, as I mentioned already in the introduction, is that these systems have extremely low magnetization, and so conventional techniques for probing magnetic order will not apply. So where does ferromagnetism in quantum Hall systems arise from? So let's first consider here the spectrum of graphene. In the absence of magnetic field, it has a relativistic spectrum. Energy increases linearly with momentum, and once we subject the systems to a strong magnetic field, Landau level develop. And we're going to be focusing on the Landau level that emerges precisely at the Dirac point at zero energy. Because the system has two different types of symmetry, one is the valley symmetry. There are two equivalent valleys for this system, and the other is spin symmetry. Each Landau level is in principle fourfold degenerate, and I show this here by 4 lines. And note that the energy of these Landau levels is flat, and this means that due to the magnetic field, we've quenched the kinetic energy. So already we see that the dominant physics that's going to govern the behavior in this system is going to be Coulomb interactions between the electrons. And what I'm showing here are two quantum variables on the right, A and B. These are the sublattices or up value, down value.
The noise has started. Can you try it again?
Yes, let me first, I'm going to.
Yeah, okay. Let's see. Still there, unfortunately.
If it persists, I'll give it maybe 10 more seconds. If it persists, I will disconnect or I'll join again.
You can go in and out maybe, and I can kick you back in if you like. Do you want to try that?
Shall we try that?
Okay, that's better now.
Oh, it's better? Okay, so let's continue. If it happens again, I can disconnect.
Yeah, no problem, no problem. We'll adapt.
Okay, thank you. All right, so as I mentioned, the Landau levels are flat, which means that there is we've quenched the kinetic energy in the system, and the dominant physics is going to be that of Coulomb interactions. We have two quantum variables, the spin degree of freedom and the sublattice A or B in the graphene lattice, or the valley degree of freedom in the lowest Landau level. It turns out that these are equivalent. Now, suppose we'd like to fill up only 1/4 of the density of states, of the available states that are available for this lowest Landau level. The simplest thing to imagine is to say, well, we're going to fill up 1/4 of each one of these Landau levels, 1/4 with spin up, 1/4 with spin down, 1/4 of the electrons in sublattice A and 1/4 in sublattice B. This will be kind of the democratic approach. But of course, the system prefers a different organization, and it would prefer actually filling out one of the Landau levels entirely, leaving the other 3 empty. This will actually minimize the exchange interaction. When all the electrons have obviously the same quantum numbers, both in sublattice and spin, that means that they, because of the Pauli principle, they do not overlap, and therefore the Coulomb interaction is minimized. So what we see here is because of the presence of magnetic field, the system would obviously choose the Landau level that has spin up. It will arbitrarily choose one of the sublattices. And here I'm just showing an arbitrary depiction where indeed all electrons are spin up and they're occupying only one of the sublattices in the system, let's say sublattice A. And as you can see, this is a ferromagnet. All the spins are aligned. They're aligned, and their interaction, neighboring interaction, is really governed by the exchange interaction. So it's a classic Heisenberg type magnet. And of course, what we know about magnets will apply. And this means that the lowest energy excitation of this bulk material is going to be spin waves. And just a brief depiction of spin waves you see on the top. When we excite the system, the spins can wiggle. They're going to be pushing one on the other to generate spin waves. And because there is an anisotropy in the system, and the anisotropy in our case here is an external magnetic field, the system will develop a spin gap, namely there's going to be a minimum energy below which spin waves cannot live, and above the spin gap energy we have typically in this particular system will be a parabolic dispersion of magnetic excitations. Now we know generically that the spin gap in a magnet would follow in a very simplest case, the Kittel law, which means that this spin gap is not only the Zeeman energy G mu B, but it is modified by the intrinsic magnetization in the system. Of course, because the magnetization in this particular system is so low, the density of electrons is very, very small compared to what you find in metals. In effect, this magnetization is negligible. And therefore, you see that in the quantum Hall ferromagnet, the spin gap energy follows the bare Zeeman energy. And this is really an important conclusion to appreciate, because very often in strongly interacting quantum Hall physics, the energies that emerge are the exchange energies, and they're strongly enhanced compared to the bare Zeeman energy. They could be a factor of 10 or even 100 larger than the bare Zeeman energy, and yet the spin gap energy for magnetic excitations are simply given by the bare Zeeman energy. This will be a telltale in our experiments. Now, of course, this would apply to both the nu equals -1, where we occupy only one of the 4 levels, but also when we leave empty one of the 4 levels. This is also a ferromagnet that has a very similar configuration to the one I'm showing, but in principle could have a different magnetic order. It could be maybe a spin down ferromagnet or a different valley. So they don't have to be the same, but nonetheless, spins would like to minimize the Zeeman energy, the energy associated with the external magnetic field. Now, there is another phase that we can explore, and that is what happens when we only have 2 of the Landau levels out of the 4 filled. And here, without going into too much details, I'm just going to depict what is believed to be the current picture of the nu equals 0 density, 2 Landau levels filled quantum Hall ferromagnet. And this is an antiferromagnet where the spins are actually pointing perpendicular to the magnetic field. The magnetic field is out of the plane. The spins are in the plane. One spin species pointing in one direction sits on sublattice A, and the other spin pointing in the opposite direction sits on sublattice B. And you can see that the spins are slightly canted out of the plane to minimize Zeeman energy without a big penalty for exchange. The interesting thing about this antiferromagnetic phase is that it breaks U1 symmetry spontaneously, namely the orientation of the spins in the plane is spontaneously chosen. And this means that the system will have a Goldstone mode, and actually the energy for spin excitation in the antiferromagnetic case is expected to be 0. And I'll discuss this a little bit more in a bit. One thing that I think is remarkable about this system is that we have here a magnetic system that can be tuned electrically from ferromagnetic to antiferromagnetic. And I don't know of many examples of magnets that we can do that in the system. So there is a fundamental interest in this system because one can explore electrical tunability of the magnetic order in these systems, and also introduce interesting phase boundaries between the various magnetic states and see how they behave. Another interesting aspect of this system is that spin wave excitations are extremely long-lived in the system. This is graphene. It has 0 spin orbit or very, very weak spin orbit. And even in conventional graphene, only 1% of the atoms, of the carbon atoms, have a nuclear spin. And so the angular momentum in this system really has nowhere to go. And this is therefore a very good candidate for exploring spin transport characteristics, such as spin superfluidity, or some of the universal properties predicted for spin systems, such as universal Peltier and Seebeck coefficients. So I'd like to spend a little bit of time to introduce how we found a way to excite these magnetic excitations in the bulk of these quantum Hall ferromagnets, and what can we do with that. So here I'm showing a very simple depiction of a quantum Hall ferromagnet. So this is a two-dimensional system. The white here you can think of is graphene. The boundaries are highlighted by these edge states. The system is tuned to a nu equals 1 quantum Hall phase, namely the bulk. All the spins are pointing up. And we have two counter-propagating edge states on each one of the edges here carrying spin-up electrons. And we're going to apply a chemical potential difference, mu, across this Hall bar. Now, in order to excite spin excitations, what we'd like to do is we'd like to have a region near our contacts that actually has a nu equals 2 state. Nu equals 2, first of all, is a completely filled Landau level, which means we have both spin species, spin up and down, and all values occupied. And this is therefore a boring state. It's just a paramagnet. But the interesting thing is that it has two edge states, and the inner edge state therefore carries spin down electrons. Because the inner edge states cannot propagate from left to right, it folds on itself near the contacts, as you can see here. Now, when we apply a chemical potential, we see that the bottom edge states carry hot electrons at chemical potential mu, and the upper and the inner edge states also, but the returning chiral edge state carries a potential of 0 because they're coming from the right contact, which is set at ground. So if we look at this circle here where the two edge states meet, we see that there is a chemical potential imbalance between the inner edge and the outer edge, which in principle should allow us to scatter electrons from the inner edge into the outer edge. There are available states for the system to equilibrate. But what you can see is that for this transfer to occur, we need to flip a spin. The inner spin down electrons have to flip in order to access the outer edge states that are only available for spin up electrons. And so this process is going to be forbidden as long as angular momentum conservation exists. So if we increase the energy, however, above the spin gap energy of the bulk ferromagnetic phase here, what can happen is that a spin down electron can in principle flip to a spin up electron by exciting a magnonic excitation, a magnon, in the bulk of the quantum Hall ferromagnet. The bulk quantum Hall ferromagnet is strongly polarized. When a magnon is excited, it reduces its magnetization a little bit. And you see that the net transfer of angular momentum goes from down to up here and here from up to down, and thereby we conserve angular momentum. Now, I want to point out that the launching of magnons at this upper left corner here is not enough for us to know that that process exists. In principle, it can exist, but what it would do is simply redistribute charge from this red edge states here on the left to the blue one. But because the direction of propagation has not changed, the way current is flowing is not changed, and therefore the conductance of the system is not going to change. We won't know that this is happening. For us to realize that something is happening, these bulk excitations must be absorbed at one of the other three corners in the system. In fact, it's not hard to see that if they get absorbed at this bottom left corner, the conductance will decrease because we're going to have less current flowing from left to right for the same chemical potential difference. And conversely, if they get absorbed on the upper right corner, they're going to increase the conductance because we have less returning current now. And in fact, when we do an experiment in a simple geometry that you can see right here, you see that the conductance here in the top panel is quantized. And once we hit the Zeeman energy shown by the dashed lines, the conductance drops, which means that for negative biases, magnons are being launched at the upper left corner. And we basically surmise that magnons get absorbed at the bottom left corner. I haven't explained why, but when the bias changes, in fact, the magnon generation site also flips corners, so it appears here at the plus sign. And in order for the conductance to decrease, as we see in experiment here, magnons need to be absorbed primarily at the upper right corner. Now, the fact that we have a mechanism that can both increase and decrease the conductance suggests that we can control this phenomena. And here we've done some control experiments where you can see that depending on the geometry, we can have the conductance either drop on both sides, both positive and negative bias. It could increase at both sides, and it could also have a geometry where it increases on one side and decreases on the other. And it all has to do with the distance of the absorbing sites from where the magnons are generated. So one conclusion that we have here is, number one, we do see the bulk propagation of magnons because they get absorbed at these opposite corners. And we can also control whether the conductance increases or decreases simply by controlling the distance of propagation. So the experimental observation here is that magnons, the phenomena is strongest when magnons need to travel a short distance. This is not something that we understand very well at the moment, but it's an experimental fact. So once we've established that magnons exist in this quantum Hall ferromagnets, we can now start doing some probing experiments to use these magnons to explore various quantum Hall phases in this system. So here's where I'm starting to discuss the use of magnons as probes of strongly correlated phases of matter. So here is a slightly more elaborate Hall bar where we still have our two contacts biased between mu and 0, which means that current is going to be flowing from one contact to the other. But I've introduced two additional contacts here. These are going to be voltage probes. And in quantum Hall systems, we know that if we measure voltage probes, the difference between the potential of neighboring voltage probes, we always will see a 0 potential because we're in a quantum Hall state and the system is in a 0 resistance and 0 conductance phase. But now once we exceeded Zeeman, we have magnons propagating through the bulk. They're going to be propagating throughout the entire system. And in principle, they could also be absorbed at some of the contacts here and redistribute again the way current is flowing near the voltage contact this time. Now, what this is going to mean is that the current equilibrium, a voltage contact basically is a condition where the incoming current equals the outgoing current. But if magnons get absorbed, here you can see, for example, that the amount of outgoing current is going to be different from the amount of ingoing current. And so potential has to change on these contacts to maintain 0 current condition. And so what we see here is that we can, in principle, non-locally detect the presence of magnons on some voltage probes that are far away. So here's the geometry that I'd like to discuss now. We have a Hall bar that has several contacts. We're going to be using two, specifically L2 and L3, to generate magnons throughout the bulk. And we're going to use contacts L4 and L5 to measure non-locally whether these magnons have arrived. And the idea of the experiment is that we're now going to put a gate here in the green region. On the top, this is a depiction of our graphene device. We're going to use top gate 2 to change the phase underneath this region and to ask, well, can magnons propagate through the bulk of this different phase that we have in the middle? So this will be a scattering experiment, but only for magnons and not for charge. So let's start by looking at the conductance as we did before. Remember the conductance, what we saw when we were just looking at the conductance between contacts L2 and L3. What we see here in a color map is on the vertical axis is the DC bias, and you see that the middle region is red. It has a conductance of 1. That's the quantized Hall conductance. But as we exceed Zeeman, the conductance changes drastically because magnons get absorbed at one of the contacts, L2 or L3. The horizontal axis here is the potential applied to the gate. So we're changing the phase underneath the green region. And you see that nothing much is happening because this is just the conductance. The conductance really cares only about the absorption of magnons at the two contacts that generate the magnons and not about what is crossing underneath this gate 1. To see what's happening underneath gate 1, we're going to look at the non-local potential at measured cross contacts 4 and 5. But before going and showing that data, let me just highlight the regions of density that we're going to be exploring. So as we vary the top gate voltage, the phase underneath this green region is going to change from filling factor -2, which is a paramagnet, filling factor -1, which is expected to be a ferromagnet, but maybe of a different type than the one that we have in the bulk where magnons were generated. Nu equals 0 is the canted antiferromagnetic phase. Nu equals 1 here is basically an unperturbed situation where the bulk, where the magnons are generated, is exactly the same as the one underneath the gate. And then again, nu equals 2 on the right here is another paramagnet where the system should not have any magnetic excitation allowed. So here again, schematically is what we're trying to do. We're going to tune the phase underneath this top gate 2 from, let's go from the right here, from nu equals 2, which is a non-magnetic phase. And you can see here both the edge state arrangement in this region. But the fact is that the bulk should not support any magnetic excitations. Nu equals 1 is an unperturbed phase. The canted antiferromagnetic phase, where you see the edge states are not even allowed to cross the region. But again, remember, we're probing the bulk properties, not the edge properties. And the nu equals -1, which is again a ferromagnetic state, but which in principle could be of different nature. And this is what our non-local measurement is showing. So first of all, you see a very strong non-local signature that strongly depends on the phase that we're exploring, the x-axis here. You also see that there is a 0 voltage measured as long as we haven't exceeded the Zeeman energy, which means indeed, if we haven't exceeded Zeeman energy, we're not generating any magnons in the system. And then we can now start looking at what happens at the various phases. So let's start with the nu equals 1 region here highlighted in red, in the red square. Note that the signal is changing sign between positive and negative bias. And this is simply to indicate that magnons prefer to absorb in contact 4, which is closer to the generation site, than it is in contact 5. And that's why the signal will change sign. I'm happy to discuss this further in the break during the questions if this is not entirely clear. But this is basically our unperturbed regions. Magnons make their way all the way from the generation site to the detection, which is these non-local probes. It's a distance of about 10 microns. And we can see a very strong signature of magnon generation that travel all the way to our contacts. If we now look to the right, this is the nu equals 2 phase. We see that largely the magnetic signal has been suppressed. We see a little bit of a signature here. We believe that signature has to do with a small nu equals 1 phase that exists between the outer edge and the inner edge that magnons can still slightly penetrate through. But largely, indeed, as our expectation is, we have largely suppressed the presence of magnons through the bulk of this nu equals 2 phase. You see the same thing happens here to the far left. Again, that's the nu equals -2 phase. Now, the first puzzle or surprise is the nu equals -1 region. Note that we see a signature that's nearly identical to what we find for nu equals 1. And this is despite the fact that now we have 3 Landau levels occupied on one side and only 1 occupied on the other side. So what's going on? So here's a depiction of how the Landau levels arrange themselves when we go from the nu equals 1 region where magnons are generated to the nu equals -1 region, which is the probing region. It turns out that there is only one way to arrange the Landau levels in such a way that the inner 2 Landau levels form a spin singlet. You see they have the same Valley index K prime, one of them is spin up, the other is spin down. That means that this is a non-magnetic contribution to the total phase, and therefore the nature of the magnetic order of the nu equals 1 and nu equals -1 are precisely the same. And this means that magnons can indeed propagate unperturbed entirely from left to right through this bulk region. Note that from the point of view of edge states, this is entirely not the case. The edge states coming in from the left, they're all reflected back. And so in terms of conductance through this region, the conductance is very strongly perturbed by the nu equals -1 phase, but magnons are not perturbed at all. So lastly, I'd like to focus on the canted antiferromagnetic phase, which is shown here in the middle. You see that this is really a charge insulator. Charge cannot propagate through this region. And in fact, we see at low biases, the suppression also of the magnetic signal. But if we zoom in, so we're zooming in.
There's a little bit of a delay from you switching the slides, like for a few seconds. I'm not seeing it, okay? Just when you talk, just keep that in mind.
Perfect. So now you saw that the red square, we're highlighting now, we're expanding the scale here. We're going to much larger DC biases and a narrower range of densities. So the dashed lines here are showing the canted antiferromagnetic phase, the nu equals 0 order. To the left, we have nu equals -1 and 1, now showing all the way to very high energies. And again, you can see the similarity between nu equals 1 and nu equals -1 that we talked about before. But now we also see that in the canted antiferromagnetic phase, we do see magnetic signature, despite the fact that charge cannot propagate from one side to the other at all. But it doesn't start at very low energies as we'd expected, even though we predicted that the spin wave excitation of the canted antiferromagnet will be gapless. So what is going on? And we believe that what's going on here is that we have an exchange bias type of phenomena, where despite the fact that the spin wave excitation in the middle here, in the upper left panel for the nu equals 0 phase starts from very low energies, on the left, we have the ferromagnetic phases, which have a spin gap, but the spins have to cant from a spin polarized phase on the left to a spin antiferromagnetic phase in the middle. And in this canting region, there's a domain wall, which is very unfavorable from the point of view of Coulomb interaction. And therefore, there is an effective barrier for magnetic excitations to propagate. And we need to exceed this barrier in order to see spin wave propagate across from one side to the other. So what I've shown here is that we have found a way in the quantum Hall system to generate magnons. We are now able to do magnetic scattering experiments by tuning the different phases. And in fact, we're expanding this now to look at twisted bilayer graphene and other phenomena and phases in layered materials where the magnetic properties of the system are still unknown and require exploration. So what I'd like to do now in the remaining 15 minutes or so is to discuss a different type of pose, maybe a generalization of what we've seen so far. So up to now, we were confined to be within graphene. We found a way to excite these quantum Hall ferromagnets. They have really interesting prospects in terms of exploring spin superfluidity and other spin transport properties because of their pristine characteristics. But we'd like to do something a little bit more generic in terms of scattering platform. And I'd like to remind everybody what is the kind of the general principle behind true scattering platforms and what are the unique characteristics and advantages. So here I'm showing a schematic of a generalized scattering platform where we have some impinging waves or particles. These could be X-rays or neutrons or any particle of interest. They're propagating in vacuum, so in a medium where these waves are unperturbed until they hit a target of interest. They interact with this target in a way that is typically described by some structure factor. And then these waves or particles get scattered out into, again, vacuum, where we can detect them far away. Now, the nice thing about scattering experiments is that we're able to learn something about the material itself without actually probing what is going on inside the material. We're looking at what happens to the scattered waves, and from that, we're reconstructing some intrinsic property of the material. For X-rays, for example, if we can measure the amplitude and phase of the scattered waves, we can deterministically determine the structure of the crystal. Similarly, with neutron scattering, we can say something about the order if we can deterministically determine the amplitude and phase of the scattered particles. In most scattering experiments, we have a way of launching waves that have a well-defined energy and momentum, and so these are done all in a momentum and energy resolved manner. And I want to also remind you that generally it's very hard to detect in most scattering experiments both amplitude and phase, and so we usually have only partial information in order to reconstruct our target, because the amplitude is much easier to extract than the phase. In X-ray scattering experiments, for example, typically we do not have access to the phase. So what I'd like to ask here is whether we can generalize what I've talked about up here in the left, where we can now generate coherent magnons that have a well-defined energy and phase, have these magnons impinge on a target, measure them somewhere at a distance where our target is no longer present, and infer something about the properties of the target itself. So here's the schematics of what we're trying to do. The thin film here is going to be some magnetic insulator, which is going to be our vacuum, if you like. It's basically a material that can support long-lived magnetic excitations. These are, this in our case is going to be YIG. Of course, there have been tremendous number of beautiful experiments done on YIG by many experiments, including book cards here. I'm going to be discussing a different measurement technique that we are familiar with. However, the concepts that I'm going to be describing are not unique to our measurement technique and can be implemented also using, for example, Brillouin light scattering. So the idea is that we're going to be launching magnons using some microwave strip line here on the left. This, as you'll see, allows us to generate well-defined, coherent magnetic excitations with a well-defined wave vector and energy. We're going to have these waves impinge on the target shown here in the middle as this circle, and we're going to be imaging the scattered amplitude and phase, in our case using a local probe, an NV center magnetometer, that will allow us to extract both the amplitude and the phase of the scattered magnetic excitation. And so for this to really work as a scattering platform, what we need to be able to show is that we know how to launch coherent waves with well-defined energy and momentum. We need to show that we can detect these waves, ideally both amplitude and phase. We need to show that these waves have an appreciable interaction with the target. And note, this magnetic insulator, our vacuum, is going to be roughly 100 nanometer thick. We're going to be depositing some material of interest on top, and we hope that the magnons will interact meaningfully with that target, and so that we can learn something about the target. And the last component will be to show that we can do a reliable extraction of some target material properties. And as you'll see, this is really the challenge currently in these experiments. So as I mentioned, one way of looking at these magnetic excitations is using NV centers. I'm going to just, 1.5 slides on NV centers. These are defects in diamond. They behave as a spin-half system under a magnetic field, and we can use them to measure magnetic fields in a variety of frequencies. Here, what we care about is measuring the time-varying magnetic field generated by these spin waves. And we'd like to be able to do it in a spatially resolved manner so that we can resolve short wavelength magnetic excitations. One of the nice things about NV centers is that you can apply this technique both to room temperature, low temperature. The technique doesn't really care so much about the temperature that you're working in. And we've been developing these probes over the past several years. You can see here in the middle a diamond cantilever. It's a monolithic piece of diamond that was carved and shaped into this platform, shaped with a pillar at the end. There is one NV center sitting at the end. It is a magnetic sensor that has tens of nanometer of spatial resolution. The pillar serves both as an atomic force microscope, but also to waveguide the light out to our detectors that allow us to determine the spin state of our sensor. So first, we'd like to show, and this is again not something that we're first in showing, but we'd like to show that the magnetic waves that are generated here are indeed coherent. So when we send a current through this left wire, the yellow wire here, the AC magnetic field generated by the current flowing through the wire excites our YIG, excites the magnet, and then launches magnetic excitations at the same frequency of the current flowing through the wire. The wavelength is then simply determined by the dispersion relation of the medium. So once we select a frequency, that also selects a wave vector, and we'll see this in a minute. What I'm showing here is that if we position our tip above this region where magnons are flowing, and note, these are propagating magnons, they're not standing waves. The AC magnetic field that is generated by the propagating magnons, shown here, B e to the I omega t plus IKX, drives spin transitions of our sensor, which allows us to detect them. Now, an interesting feature about two-level systems, if you recall, is that in the rotating frame, when they're subject to a time-varying magnetic field, is that the spin is going to be processing from the North Pole to the South Pole, from the 0 state to the -1 and back, as you can see here, these oscillations. But the axis of oscillation depends on the phase of the driving oscillatory magnetic field. And you can see that this phase here, e to the IKX, is position dependent. So what this means is that the spins are rotating from the North Pole to the South Pole, but whether they're rotating in one axis or the other axis will be position dependent. If we're only detecting what is the projection on the vertical axis, we won't know that this axis is changing. So if we want to know that indeed what this phase is, this IKX is, we need to introduce a reference signal. And the way we do that is by generating another source of magnetic field that is not spatially dependent. This is this loop antenna that largely only drives the NB center. It doesn't drive the magnet because it's a very uniform magnetic field, and that uniform magnetic field can only drive the long wavelength excitations in the system that are now off resonance. So if you look at the rotating frame, you see that we have two contributions to the axis of rotation. We have the magnon field, whose phase here, phi, depends on position, k times x, and we have a reference field for the NB. And so these two interfere destructively and constructively to change the rate of rotation of the NB center, and this is what we can then image that now shows precisely the phase fronts of these magnetic excitations. So what you're seeing here is a movie where we're changing the phase of the reference beam, and this basically highlights different phase fronts of these propagating magnons. I want to again emphasize that what you're seeing here is wave fronts, constant phase wave fronts that we select even though these magnons are propagating. And so this demonstrates that we can not only determine the amplitude of the magnetic excitation, we can also determine their local phase. And from just looking at this panel, reading the separation in space between these wave fronts, we can determine the wavelength. And since we know the frequency, we can immediately reconstruct the dispersion. And you see it on the right here, the dispersion, the energy versus momentum. And you see that it agrees very nicely with what is known to exist for YIG through a variety of measurements that have been done and theory that is very well established for these thin films of YIG. So now we're ready to discuss the scattering experiment. And as I mentioned, we want to determine both amplitude and phase. In principle, we need to do two experiments in order to determine them. And so the first experiment we're going to be doing is one where we shut off our reference antenna. So I've kind of turned off the reference antenna, which means that now we have magnons that are generated by our strip line. They're propagating as plane waves. They hit the target. The target is going to generate secondary waves. And I haven't mentioned what this target is. This target is a different magnet. It's permalloy that's just directly deposited on top of the YIG. And in this bottom right picture, you see the circle, that's the target. This target is now generating secondary waves that interfere with the incoming waves, but because the phase of the secondary wave are locked to the impinging wave, we see that the picture is very, very clean. We see a change in the intensity of the magnetic waves. They're confined to these cones. This is something that has to do with the property of the dispersion of magnons in YIG. And this gives us the first measurement of what we call the amplitude measurement of the scattering waves. And look, you see that measuring the signal on top or nearby the magnet itself, our target itself, is complicated. The nice thing is that we're going to be using only the signal in the upper half part of this image in order to try to reconstruct some property of our magnet. Now, the second experiment that we're going to be doing is we're going to turn on the reference antenna, which will allow us to determine not only the amplitude, but also the phase. And the use of these two images should in principle tell us something unique about the target. So here you can see what happens when we turn on also the reference signal. And now you can see all the phase fronts. You can see that far away from the target, the wave fronts are indeed linear and they're propagating. The target itself is generating a wake of scattered waves. And these are interfering with the incoming waves to generate these shifts in the phase fronts and variations in the intensity. And so the question is, okay, so we've demonstrated we have an appreciable interaction between the target and our magnons. The question now is, what can we learn about the target? And this is where I think we have quite a bit of challenges, and a lot of theoretical work still needs to be done to do this properly. But I think this is a very promising platform to unravel interesting properties about the target. So first of all, let me tell you what it is that we expect. So before, generally, because we're measuring both amplitude and phase, in principle, if we know everything that we need to know about the structure factor of the scattering process, we can reconstruct directly what the target is. Of course, there is noise in the measurements, and there are deconvolution processes that exist in the system. So doing this inversion process is very hard, and we're still working on it. What I'm going to show today is the inverse process, where we're going to be suggesting a model with various parameters, and we're going to be tuning these parameters to minimize the difference between the prediction, the model outcomes, and the scattering and the measurement. So what do we expect for the model? So remember, what describes this system is basically Maxwell's equations, nothing more. The system has a finite magnetic field in space, and we're exciting it with a time-varying component. The system has a magnetization, and it has a magnetization that wants to respond to this time-varying magnetic field. We're going to be only looking at the component of magnetization that's responding to the impinging magnetic excitation. Now, in the limit where the wavelength of the photons in vacuum is much, much larger than those in the medium, namely the magnon wavelengths, we're in what's called the magnetostatic limit. And the Maxwell's equations, therefore, have a very simple form that are shown here on the left. And the magnetization is simply given by some static component plus a perturbation that's due to the magnet itself, to our target. Now, because we have the curl of this magnetic induction equals 0, we can describe this system as a scalar. And what we need to solve is basically this Laplace type equation, where we have a source term on the right who's given by the divergence of this responding component of magnetization of the target. So what I'd like to show is, what do we expect for this target to be in this Laplace equation? So our static magnetization, let's say, is magnetized in our target pointing to the left and in the plane. This means that the response of this magnetization to an oscillatory component can only be perpendicular to it, because it's already maximally magnetized in the direction of magnetic field. So delta M of the target is going to be only in the y direction. And our target, as you can see here, is given by the divergence of this magnetization, which means that it's going to have a dipolar shape. It's going to be positive on the top and negative on the bottom. And we're going to therefore try a moment expansion of this target, starting from the dipolar contribution, then adding a quadrupolar, etc., to see whether we can mimic the response of the system. So this is the last slide that I'm going to show. And what you can see on the left is the experimental measurements. The upper panel is the amplitude scan. The bottom panel is what we call the phase scan. The middle panel is the simplest possible model that consists of only a dipole. And you see these small insets.
Wait, because we still don't see it. I think it's still coming. There's some delay a little bit of when your slides show up. The data itself, we only, okay, now we see it. Perfect.
Okay, so on the left here, let me just repeat, this is the data that I've already shown. The upper left is the amplitude, and the bottom left is the phase scan. In the middle, I'm showing the simplest possible model where we model our target as a dipole. And you can see it's a continuous dipole. It's kind of smooth with Gaussians. It has a positive lobe on the bottom and a negative lobe on the top. And in principle, it could be imaginary or real or both. And we're using both here. And what you can see is that for this target, we're getting something that kind of captures a little bit of what the experiment is showing. Namely, you can see the bending of the phase fronts in the phase map, and you can see some modulation of intensity in the amplitude map. But the modulation and intensity in the amplitude map is very weak compared to the experiment. And also, there are not enough details in the phase map to compare with the measurement. The right two panels go to the next level where we've now introduced a quadrupolar contribution, and you can see how the target now looks a little bit different. It has a slight quadrupolar contribution in the imaginary component. And you see that now we're capturing better what happens to the phase fronts and some of the discontinuities that you can see in the phase fronts in the measurement. And also you can see in the amplitude scan a little bit more realistic modulation of the amplitude. I have to say this is the best that we've been able to do so far in reconstructing the target. And you can see that it has some non-trivial information about the target, namely that it has this dipolar shape with some quadrupolar contribution. It's not something that we would have been able to determine just by looking at the target itself. But I think that in this kind of reconstruction process, there is much more work that needs to be done to really take the full advantage of this system. I can also say that we've replaced our target and put down just a non-magnetic material like a copper disk, and we see very nice scattering of magnons of this copper disk as well, likely due to the induction of currents in the disk. And these currents are generating, again, time-varying currents are generating time-varying magnetic fields that are again launching secondary magnons in the system. So I'm really optimistic and excited about these new scattering platforms as ways of exploring magnetic properties of systems of mesoscopic scale. Again, here, the importance is that we're able to look at some properties of a very tiny system. This is only 30 nanometer thick of permalloy, a few micron size. This is not something that typical magnetic techniques, measurement techniques will apply in order to discover the underlying properties. So with this, I'd like to summarize and show, basically just acknowledge the contribution of the students and postdocs who have done all this work, and really thank you for your attention, and take some questions if there are any.
Okay, thank you. Thank you very much, Amir. I think everybody raise their hands to clap. I guess that's the only thing we can do here. You can see on the right, you can see all of the people raising their hands in there. It's a big clap in there. So there's about, I think we're all together at the high peak of 400 people in between here and YouTube. And now, please lower the hands and only raise them if you actually would like to ask a question. So I guess Oscar is going to be the first one. Let me ask, get Oscar to, I'll unmute you. Okay, hang on a second. Allowed to talk, okay. Oscar, go ahead. You should be able to unmute your microphone now and ask the question.
Hi, Amir. Is it possible to use these techniques to measure the energy momentum dispersion of the magnons?
Yes, so I've shown this. Again, I want to emphasize that measuring the energy momentum dispersion of magnons in YIG has been done. It has also been done in other materials. Here, what we're really hoping that, Okay, I think what you're asking is, suppose I put some target material on top of YIG, can I then measure the energy momentum dispersion of that of the target itself, and not the medium that the magnons are being launched in? Is that right, Oscar?
Yeah. So for example, let's say in a twisted bilayer graphene at the magic angle, we have an insulator. There could be some interesting dispersion to the magnons. Is there a way to measure that? That's basically what I'm thinking.
Yes, so I believe there is, because what's going to happen, you know, it's going to be very similar to what you find in normal, let's say, neutron scattering or any other scattering technique, right? So we're impinging with magnons that have a well-defined energy and momentum. And suppose this energy and momentum does not agree with the energy and momentum of the excitations in the material that you're interested in, then likely what's going to happen is that you're going to see some evanescent behavior of the magnetic excitations through this medium. And I think we should be able to extract it. But again, as I said, right now we're working hard together with a group of Eugene Demler to work on this reconstruction process and basically extract the properties of the target. I can say largely that what the reconstruction involves is basically extracting the magnetic susceptibility of the material. And that has information on the dispersion itself.
Yes, thank you.
Let me ask, by the way, please do not ask the questions in anonymous, because I don't have a way to actually give the microphone. I don't know who you are. There's a question here. Well, let's ask the question directly that is written there. Is it possible to do quasi-particle interference measurements in magnons in ferromagnets, like exciting two ferromagnets that will be coherently interfering? And I think the answer, you've already kind of shown some experiments, but go ahead and answer that. If you...
Yeah. So again, in YIG, this has been done. People have shown that, you know, magnons in various geometries will diffract. There have been some beautiful experiments coming from Hillebrand's group and other groups using BLS to image magnonic scattering, etc. Recently, there's been also a nice experiment coming from Delft, from Tuno van der Sar's group, on the interference of magnons in YIG and their detection, again, using NV centers. I think, again, the interesting question is, can we do that experiment and learn about the interference of magnons in the target material? Because YIG, you know, we have a very good understanding of YIG. The whole point here is to use YIG as our vacuum and have that interact with the target material of interest. And I think, yes, if you have a target material of interest and you can devise a situation where the magnons, the excitations of that material interfere, let's say you create two holes in the target material or something like that, I think we should be able to extract information about interference phenomena in these materials as well. So I'm very optimistic. I don't really see at the moment where the limitations to such experiment would come from.
Okay, let's ask Tobias Meng. You have your microphone on. Maybe you can ask your question.
Yeah, so thank you very much for this nice talk. I was wondering about the dimensionalities of the targets that your techniques is best suited for. Is it mostly layers or yeah?
Right, so of course, this is kind of a very good question. So one, the interaction of the target with the magnons in YIG is via the surface, basically. These are surface magnons. The interaction is either through the exchange interaction, namely the material sitting directly spin-to-spin interaction, or dipolar interaction. I think both are interesting to explore. Currently, this experiment that I've shown here is largely a dipolar interaction, but I think there will be a different structure factor associated with the exchange interaction. Yes, we're really targeting this platform for layered materials, or any other thin films that you can deposit on top of YIG. Of course, if you put something that's very, very big, very thick, then these surface magnons will not interact with the entire medium, and so the response will be weak.
Okay, Marcus, I think, can you unmute yourself and ask the question next? And then...
Marcus Gast here. Thank you for your talk, for your interesting talk. I have a question concerning this scattering experiment. Is this purely elastic scattering, or are there also inelastic scattering processes that could be important? Because the target, as far as I understand, is also pretty complicated.
Yes, and I think that's the whole point. Yes, I think that's a great question. You know, what we can detect is not only, you know, what we see, for example, is that the target itself absorbs magnons. So, for example, when we do the experiment with copper with a non-magnetic material altogether, what you see is that the intensity of magnons that you find on the other side of the target is weaker than what you find below. So it's not only that there are phase shifts associated with the scattering process, there's also absorption, namely inelastic processes. So yes, the susceptibility of the medium has both a real and imaginary part, and we, in principle, can address and extract both. Okay.
Let me ask Burkhard, I think you have a question, yeah?
Yes, I do. Actually, I have two questions. Number one is we have studied this effect with phase-resolved Brillouin light scattering, and we call it actually caustics. You didn't use the word caustic, so because it's just the fact that the isofrequency curves are absolutely flat if you have such a scenario with such a small dot. Actually, we were even able to see that if you simply drill a hole, because what matters is the scattering object is just the local dynamic stray fields which you generate. And you can generate it, of course, with some permalloy disk. You can simply create it just having a little inhomogeneity, such as a hole in the Yig film. So why don't you call it caustics?
So you could, well, caustics describes the properties of the medium itself, of the Yig itself. And yes, I agree. The fact that you see a cone shape has to do with the dispersion nature of the magnons in Yig. Mm-hmm. This is really not the purpose of this study. The purpose of this study is to say something about the target, not about the Yig. In fact, we need to use every bit of information known about Yig in order to be able to reconstruct what the target properties are. So we're using the fact that indeed we have the knowledge about the caustics and the dispersion and the isofrequency contours of the dispersion of the Yig. But the whole point here is actually to go back and say something about the target. So I think that's the exercise. The exercise is not to say something new about the scattering medium itself, Yig. There is nothing Yig, nothing new here. This has been studied beautifully by your group and by others. And so it's really that serves as a point of entry to this process.
And that is especially my problem here, because if you have this permalloy disk there, you rely on the reference wave, which is just a plain wave generated by your loop antenna, isn't it? And that is certainly the reference wave is very much disturbed by this permalloy disk. So you have now two locally varying fields which are interfering in your case.
Right. You're precisely on target. This is the whole idea. So if you didn't have the permalloy there, these plane waves will propagate unperturbed. Having the permalloy there perturbs them. And the exercise that we're interested in is what can we learn about Yig? Sorry, what can we learn about our target in this particular experiment, permalloy, and the other experiment, this is just copper. What can we learn about our target?
Sorry. I was talking about the inhomogeneity in the uniform reference field, which you generate by the permalloy disk.
Yes, so this is another, so yes, that's true. This is something that the model should include, the fact that, for example, let's imagine that, so our model only effectively includes exchange interactions. So basically there is no non-local interaction. Now it's true that the presence of permalloy there changes the magnetic fields in this region. And so the Yig surrounding this magnet in the static limit, even without waves, sees a different magnetic field and its spectrum is therefore different. So this is something that in principle needs to go into the model when describing how this magnons scatter off the target if we want to have a reliable construction and reconstruction. And this is something that we're including right now. For the copper disk, for example, it is not generating any magnetic fields in DC, and yet we see very strong scattering of magnetic waves. And so the dispersion of YIG is not altered at all in the vicinity of the copper, and yet it scatters wave. And again, it has to do with the magnetic susceptibility of copper.
Yeah, but the local reference microwave field.
We have a lot of questions still pending. We cannot go to.
I'll drop an email.
Okay, yeah,
Yes,
that's better.
let's discuss this further. This is a very interesting and useful discussion. I think figuring out a reliable way of reconstructing the target is really something that I think would benefit the field now.
Yeah, it's very challenging. Ali Reza, you have a question?
Yeah.
A quick one, please.
Yeah, it's a very nice question about the first part of your presentation about the transport at nu equal to 0, which is an easy plane antiferromagnet. I'm wondering that in this case, because is it possible that spin is transported by superfluidity? I'm wondering that if it's possible to see phase slip in your experiments.
So currently, in the first part of the talk, I did not talk about any time domain experiments. I think for us to be able to say that there is a superfluid phase, yes, indeed, I think we would want to see some kind of a coherent mode. And one way to determine it would be to see that the underlying excited magnet, this canted antiferromagnet, has a well-defined phase. This is not very easy because number one, magnetization is very weak. So I don't even imagine
challenging even for any sensors to detect.
The noise is coming back up. Can you check that? Okay. Sorry. In the meantime, by the way, we still have a few questions left. I'm going to try to get around to everybody while Amir is trying to figure out the technological aspects of these things. Because there's a lot of interest on a few things from Leonid. We have questions. But Leonid, by the way, that's yeah. Go ahead. Can you talk now, Amir?
Yeah, is it better now?
Yeah, it's better. It's better. So Andrew, you had a. Go ahead. Did you finish the question? You answered to Ali Reza?
I think so. I think that the challenge is really to develop a local probe. I think that would allow us to see the local phase of the magnetic excitation in these quantum Hall ferromagnets. This is something that is challenging, but would be a very interesting.
So the next question is from Andrew Kent. Andrew, go ahead and ask a question.
Oh, hi, Amir. Thank you for that very interesting talk. I had a question. It seemed in the case of the scattering experiment, you excluded exchange interactions, if I understood properly. Were those excluded in your analysis? That is, you didn't consider exchange between the permalloy and the YIG?
Right. That's correct. We've basically tried to
start with the simplest
in the system, I think that we definitely do need to take this to the next level in modeling how the static properties of our target affects our medium.
If you like, you can think of the medium.
Amir, 1 second. I think there's some interference with your. I wonder if your kids are playing with something. Try it again. I don't know what it worked before when you resetted something.
How's it now?
Oh, it's still there, unfortunately. Okay. The challenges sometimes.
Still there?
Now it's better. Yeah.
So Andy, I think the simplest way to think about it is let's take all the perturbation that the permalloy introduces, including the static effects of it onto the YIG as the target. So there is something here that you can draw kind of a dashed circle around it. If I were to, I don't know if I can annotate here. If I can annotate, I would draw, some kind of a circle, let's say around like that.
Mm-hmm.
say, hey, this is the target. This is the thing that's scattering magnetic waves. By measuring what's happening in the far field, we don't know anything about the target, zero. The only thing we know is the far field dispersion of YIG, which is unperturbed. And this is, back to Burkhardt's question, all the caustics, etc., goes into that. And by measuring the phase fronts and the amplitudes in the far field, we can reconstruct a target that encompasses all the interaction, exchange, dipolar, everything that exists in this region. Now, if you say, okay, that's great, now how can we decompose it? That's where the challenge comes. There's going to be a decomposing because of what Burkhardt asked about the static modification of the dispersion of YIG near the permalloy. There could be exchange contribution, dipolar intribution. All these contribute to the scattering process.
Mm-hmm.
Okay.
Okay. Thank you.
Very good. Sorry, Philip. So Philip has another question. Philip, can you unmute yourself? And
yes, can you hear me?
Yeah.
Yeah. Thanks for that very interesting talk here, Philip here from Kaiserslautern. I would first, before I ask my question, maybe a short suggestion. Did you check in your experiments for non-reciprocity by simply changing the direction of the external field, if you're talking about the scattering?
Yes. So, we could image the magnons, and you could see that you can barely detect magnons when they, in the opposite direction of the wires. So yes, there is strong non-reciprocity, and the waves that we're using in these scattering experiments are the surface waves that are on the top surface interacting with our medium, and we rarely see the reverse. Yeah.
No, that's very good, because that's what we would expect. But what we would expect is, since you have YIG and permalloy, that constitutes effectively a magnetic bilayer, and there will be a common dispersion. And if you are propagating perpendicular to the static magnetization, the propagation, let's say up or down, will have a different wavelengths at the same frequency. So the dispersion relation is non-reciprocal, and maybe that can help you to analyze the scattering.
Yeah, I think that's absolutely correct. I mean, I think, so, in relation to the previous two questions, right? If you take the scattered amplitude and you basically say, okay, what kind of superposition of sources, delta functions, let's say, do I need to introduce in order to generate my scattered amplitude and phase? You're going to get something. And now you can ask, well, okay, how does this relate to what I know about the materials themselves? And in this case now, you might find that, yes, you need to introduce non-reciprocity in this magnetic bilayer, etc. So all these things need to go into some theory that eventually needs to be consistent with the scattering amplitudes and phase that you're measuring. But yes, I agree that the whole purpose of this exercise is to learn about this underlying physics, not necessarily to assume what's going on and then see if it's correct. This kind of approach is still hard. It's hard because the inverse problem always, because the data has noise, you can't just simply invert the measurement to produce a target. In fact, there are going to be a lot of targets that are consistent with the measurements to within the noise that the measurement has. And so, yes, I think what you're suggesting is to suggest some models to see how these models generate scattering patterns and to minimize these predicted scattering patterns with a measurement to hone in onto the relevant physics is the right approach. I agree.
Gisela, do you have a question?
Can you hear me?
Yeah, you can hear you.
So thanks for this nice talk. I have a question concerning the resolution of the technique. So the picture you showed, this is a very large object, a very easy object. It's 4 microns, and the wavelengths are relatively large, maybe in the order of microns. the tendency to go or to image a smaller and smaller object is related to the resolution of your experiment. How far you think you can go in a spatial resolution for reconstruction or whatever.
Great. So this is a great question, and it has kind of a variety of answers. So number one, kind of the ultimate limit of the spatial resolution of the technique will be the NV center itself and how far it is from the target. This is typically on the order of 10 nanometers, so we shouldn't be able to see something with higher spatial resolution than that. But there are other limiting factors. For example, if the target itself is, let's say, 100 nanometer thick, then obviously we're going to be imaging this target at some distance above the YIG. And so this means that if we're only looking very far away in the far field, we should be able to image again within 10, 20, 30 nanometer spatial resolution. If we want to image above the target, we're going to be with a little bit lower spatial resolution. Number three, if we really want to push this technique to its ultimate limits, we would need to be able to also generate magnons with these kind of wavelengths. And this is not very easy. It would require going to very thin YIG films. And so we haven't pushed this very, very hard at the moment. With 100 nanometer YIG film, in principle, you should be fairly easily able to excite wavelength down to about 100, 200 nanometers. We haven't pushed this really hard at the moment. There are many, many things that we need to work on with this technique, but I think that going down to thinner YIG would allow us to push the wavelength of this system. And this doesn't mean that the target needs to be 30 nanometers in diameter. It could be long, but basically exploring the target properties with different wavelengths eventually will teach us about the magnetic susceptibility as a function of Q and omega of the target itself.
And maybe short question, to what frequencies you can go?
So the range of frequencies is, the ones that are relevant for NV centers. So they're in the few gigahertz range. I don't believe we can push it to much higher than that. One of the nice thing about the surface modes of YIG is that you can vary the wavelength of the excitation without, over a very broad range without varying the frequency that much. So I think in that sense, this is a very nice property that we should be able to change wavelength within the frequency range that is of interest to us. But again, there is much work to be done here.
Okay, thank you.
Hans Hübel, you have your...
Yeah, thank you for your really kind of stimulating talk. I liked it a lot. I have a question regarding you said that you learned something about the target, but my question is, can you disentangle between the properties of your scatterer and the properties of the interaction of your YIG wave, of your spin wave with your scatterer?
No, so I think the answer is that any perturbation to YIG will produce waves, and if I had a delta function, some perturbation like Burckhardt suggested, you drill a tiny hole within YIG, so you just remove some material, you will see a pattern that's consistent with a delta function of a scatterer. It's like in any medium, right? If you take light and you scatter it off some material, and that material has a different dielectric constant, in addition to having some interesting excitations like excitons and whatnot, all these things go into the scattering process of what you'll find in the far field. You can't disentangle that. So the fact that the medium in the scattering region changes its properties is part of your target. I think in the process of reconstruction, it would be interesting to try and disentangle the various components, but I don't think one can speak of a target completely separate from the vacuum or the space that it is sitting in, because as many people already questions have been asked, all these things affect the properties of the medium. And so you have kind of a combined, your bare target plus the YIG that is surrounding it is effectively your target.
Okay.
Okay, thanks.
Yang Xiao, you have a question?
Just I want to ask, in the first part of the talk, is there any information about the magnon diffusion length in the μx1 and ferromagnet region and the μx0 antiferromagnet region, the diffusion length basically for magnons?
Thank you. Very, very interesting question. We don't really know the answer to that question. So there are a few things that we do know. One is that our signals, which are electrical at the end, we're measuring some voltages on electrical contacts, etc. They diminish with distance. However, they diminish fairly slowly. So we can easily detect, remember the magnons that are being excited in this quantum Hall system are magnons of wavelength that, down to a magnetic length or so. So on the order of maybe 10 nanometers. And the entire range. So all the way from very long magnons to very short wavelength magnons are being excited. What we see is that they can propagate over macroscopic distances, tens of microns easily. Their intensity becomes smaller, but remember, every time there is a contact, that is a magnon drain. That's where magnons get absorbed. So an interesting experiment to try would be to just have a 4-contact geometry where you just make different devices where you increase the distance between the generation site and the absorption site without having any additional contacts in between. I think this is very interesting because one of the predictions of the spin superfluidity is that the intensity of the spin current going from one side to the other should decay rather weakly with distance. So I think this would be an interesting experiment to try. But again, I don't have the answer to it. The other thing that I can say is that when we see magnon transport through the canted antiferromagnetic phase, the signals coming through are rather weak. And I believe it has to do with the fact that this is a bucket. It's like a trap for magnons. Magnons that are propagating above our exchange barrier, in principle, can relax and then they can't escape. So they're kind of stuck there. And so I think the diffusion across this region, we're not probing it the way I'd like to. And so I suspect that right now, not a lot of magnons are making it through because of this region. But again, I don't really have good measurements to determine, the answer to your question. What are the diffusion lengths?
Okay, another short question. Are the magnons are exchange magnons or dipolar magnons or both?
In the quantum Hall system, they're nearly purely exchange magnons.
Yeah.
Okay, yeah, thank you.
I have actually, Sasha, I think, has a question as well, but in a second. A quick question, or have you tried in the 90s, we had a lot of studies, particularly in the semiconductors, because they have a lower G factor, I think, the tilted quantum Hall ferromagnets with the tilted magnetic field, that you could actually have a very large phase diagram that way to actually change them from ferromagnet to ferromagnet. Is that something that is available to you in this graphene system, or is the G factor too large?
No, on the contrary, I think that would be very, very interesting because, for example, in the nu=1 phase, when you apply, when you put a very large in-plane magnetic field, you might get much larger skyrmionic contribution. So the underlying magnetic excitation of the system would be different. In fact, some of the physics that we're seeing right now is likely due to the trapping of magnons with free charges in the quantum Hall system. So, there's a lot of phenomenology that we have that is not yet published, and I didn't have time to talk about it.
But the one that you presented was only out of plane field, right?
Yes, what I presented all out of plane, I think will be very, very interesting to change the phases of in-plane. In fact, experiments we're doing right now is to do the same experiments in bilayer graphene, where now you could change the electric field between the layers and tune into different phases just by electric field. And we already see magnonic signatures in the bilayer, and we're developing the platform to do these kind of electric field control of the various phases. So yeah, I agree. In plane and also electric field control.
Okay. So one last question from Sasha, and then we'll wrap it up.
Okay, it is Alexander Serha from University of Kaiserslautern. He has a question to the last, this characterization of target by scattering of spin waves. And for me, that the dynamics of scattered spin waves is very complicated. It takes into account the different types of targets, magnetization dynamics in magnetic target, eddy currents in metal target, the magnetization fields in geometrical defects, non-reciprocity effects, magnetically induced anisotropy, other such complicated issues. Do you expect that you have enough information from the scattered spin waves, from this phase and intensity patterns, in order to restore the information about the different kind of targets?
So, okay, so I think, so let me answer kind of, give you an in principle answer and an in practice answer. So in principle, basically there is a unique, we're measuring, so remember our target is a scalar. It's some divergence of magnetization. So I'll comment on that in just a minute. But, and it's a complex target, so that's why it has a real and imaginary component. And that's why we're doing 2 measurements to reconstruct what the real and imaginary part of this target is. And assuming we know everything that there is to know about the spin wave dispersion of YIG far away from the target, I think the answer is in principle, yes. Mm-hmm. There is a unique target that would produce the scattering waves in the far field that one is measuring. Because this is just, it's a property of this differential equation. There's only one scalar, complex scalar, that will produce precisely the scattered waves in the far field. Now, I agree with you that whatever this target is, that in principle can be extracted from this measurement technique, will include a lot of interesting physics like defects and the type of interaction with the YIG, whether it's dipolar or exchange, and eddy currents, and a variety of things. And whether we could really disentangle the contribution of all these to arrive at this scalar is a very hard question. But there is one target that does it. Now, if you say, well, actually, I'm interested not in the scalar, but in the magnetization of the target. So I'm interested not in the divergence of M, but M itself, the answer now is not unique. There are actually many magnetizations that will produce the same divergence. Obviously, any curl will do that. And so, so the answer is then not unique. So what is unique is the scalar target, in principle, is unique. The magnetization itself that is generating is not unique. And I think the challenge that as I said, is going to be to disentangle the underlying physics contributions to this scalar in order to highlight the interesting physics. But nothing in this process is any different from any other scattering process that you know of light or neutrons or any other thing. These are the challenges of scattering platforms.
Okay, thank you. And one technical question, would it be help maybe for you to analyze the scattering patterns when you will change magnetization direction? For example, if you will go to perpendicularly magnetized films with isotropic spin waves in such a case to reduce the complexity.
I think that's absolutely correct. I think having a medium with a simpler dispersion would be very nice. The practical challenge in our experiments, but maybe your experiments will be with BLS, would be a better approach for this, to basically try and magnetize the film out of the plane. For us, it might require too large of a magnetic field that would be not along the NV direction, and so might provide some experimental limitations on using NV centers as the measurement technique for extracting information about amplitude and phase. But I think conceptually, I like your idea a lot.
Thank you very much for your answer.
Well, I think that was a very good round. Thank you very much. Everybody should raise their hands to thank again Amir for a wonderful talk and taking a lot of time with the questions and answers. And with that, I think we look forward to other talks coming up. And Amir, I wish you a very good time in the mountains that with this very nice background. He's the only one that doesn't have the virtual background in there. Looking very nice. And thank you, family, for putting up with all the noise during the morning wake up time. And with that, I wish everybody a good week and hope to see you next week in the seminars back again. And Amir, if you'd like to say a few words, just to wrap up.
Yeah, I'd like to just say thank you again. I think that you know, what's typically very hard with these Zoom talks is not having an engaging audience, but I've really enjoyed the discussion, the interaction, the questions, and so I think this was kind of a correcting experience for me in giving Zoom type talks. So thank you for that.
Wonderful. Okay, great. So thank you very much, everybody, and have a great time and stay safe. Okay. Cheers. Thank you, Amir. That was great. I'll stop the recording now. Hang on.
Good.